Welcome, everyone. Thank you for coming to today's RIS Public Talk. Today is a special talk. Our speaker is the Caroline Herschel Prize Lectureship winner from 2024. The lectureship was established by what is now the Herschel Society in association with the Royal Astronomical Society to celebrate Caroline's memory by supporting promising women astronomers early in their careers. Caroline, William's younger sister, started out as his assistant, but in time became recognized as an important astronomer in her own right. She was the first to be paid as such and was awarded the RAS Gold Medal in 1828. Our lecture prize winner is our speaker today, Dr. Heloise Stevance, and she is in her second postdoc at the University of Oxford after several years at the University of Auckland. She began her work in observational astronomy with spectropolarimetry in her PhD, then became an expert in theoretical population synthesis in Auckland, and is now an independent fellow applying machine learning techniques to time domain astronomy as a Schmidt AI in Science Fellow at Oxford. Please welcome our speaker, Dr. Stevance.
All right, thanks very much for the introduction. So you don't need fancy equipment to do astronomy. People successfully sailed the Pacific using nothing but their eyes and their knowledge of the stars. But with new technology, you can open a new window into the universe. The invention of the telescope allowed Galileo to find the moons of Jupiter. The invention of photography brought astronomy into the Industrial Revolution and allowed us to start creating sky surveys on a scale that we'd never seen before. In the second part of the 20th century, the invention of semiconductors allowed humans to control the flow of electricity on a really small scale. This turned computers from things that fit into a large room to something that fits on a desk. Semiconductors also allow you to turn photons into electrons, to turn light into electricity. That's basically the invention of the modern camera. The second part of the 20th century also brought us rocketry. And with rockets, you can send out artificial satellites. Some of these can be telescopes. Now, the advantage of having a telescope in space is that it's not obscured by the atmosphere. The atmosphere is a big, beautiful blanket that shields us from some of the harshest radiation in the universe, but it also makes us blind to some of its most beautiful colors, and it gives us a bit of a blurry view. Now, one of the prime examples of how good a view of the universe we can get from space is the Hubble Ultra Deep Field. It's a little bit bright, but you can still see some of these beautiful colors on here. This is only a small portion of the ultra deep field. That's a portion of space that is 10 times smaller than the moon that Hubble looked at for 1 million seconds. The cropped down version you've got here is maybe 100 times smaller than the moon. And each of these blobs of color is a galaxy out into the universe. Now, the deep field was so successful that we've become adjusted to doing routinely with new telescopes, and the James Webb, when it went out into space, made its very own and released it within a few months of being up there. And again, you can see here loads and loads of these beautiful galaxies, and some of them even stretched by galaxy clusters in between us and the host. Now, the reason for this introduction is, one, I wanted an excuse to show you some beautiful pictures that we've taken with these telescopes. But the other reason is I really want to impress upon you that progress in modern astronomy is a partnership between people and new technologies. And that's the theme I want to explore with you today. With my job, I'm very, very lucky that I get to travel the world. And earlier, 6 months ago, in the middle of last year, I went to Chile, to the Observatory of the Sea, to observe with this beautiful tin can we call the New Technology Telescope. Now, the most observant in the room may notice there's a lot of clouds in the sky. Not ideal if you want to do optical astronomy. Fortunately, those clouds were very quickly swept away by extremely powerful winds that started battering the mountain and made it impossible for us to open the telescope without damaging the equipment. So I had a lot of time on my hands to twiddle my thumbs and take pictures with my phone. Now, this image of the Milky Way was taken with this very phone that is counting down the minutes right now. And you can see here the center of the galaxy, that is the brightest spot, and you can see maybe some cloudy looking shadows, which are clouds in our Milky Way itself, dust and cold gas obscuring our view. Here we have a slightly better view of the Milky Way with colors and better definition on the clouds. And if it was a little bit darker in here, you would see many, 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 many stars. Now, those of you that have ever been to a dark sky reserve will know that the Milky Way does not look like this to our eyes. It never does. And that's because your eyes just cannot see as well as a camera that takes an exposure of 5 minutes or 10 minutes or whatever it may be. Your eyes at best can see a few thousand stars in the night sky. A camera like the one we have on Atlas, the sky survey that we work with, can see 1 billion sorted. Now, it's very difficult to picture the difference between a few thousand and 1 billion, but we can get an intuition for it using the concept of time, which we have personal experience with. So a few thousand seconds is the time it's going to take me to deliver this talk. 1 million seconds is about 11 days. 1 billion seconds is 32 years. So long story short, the sky is really big. And not only is it big, it's also ever changeable. There's a lot of stuff that changes, such as variable stars. Here we might even see Betelgeuse. She's red, she's gorgeous, and she changes brightness super regularly. Closer to the Earth, we've got asteroids, we have comets, and much, much, much further away, we've got a plethora of stellar explosions, some of which we will look at today. Now, in this slide, I want you to focus on the timescales that I've written there. So we've got some days, weeks, hours, days, minutes, sometimes months. Those are the timescales on which these objects change brightness significantly or just look different. These are the timescales on which we want to take another picture so that we can do science. And so what that means is that not only do we have to map the skies across its vast expanse, we have to do it over and over and over again. We have to do it across space and time. Now, being able to do both, the spatial extent and the time dimension, is something that astronomers have only been able to do since the 21st century. And it's the kind of stuff that Atlas, the sky survey that I work with, does. So Atlas is the Asteroid Terrestrial Impact Blast Alert System. It is funded by NASA primarily to find and track near-Earth asteroids, particularly the ones that could be dangerous for life as we know it. To do this, it's got 4 telescopes across the globe. We've got 2 in Hawaii, 1 in Chile, and 1 in South Africa. So that gives you a sort of 360 view. But the 360 view is not enough. You have to do it quickly enough, right? And so to do it quickly enough, Atlas has a very large field of view. Now, you can't see this, but I'm going to mime it for you because I'm French. So this is roughly the size of the picture that Atlas has taken. If you catch your mind back to the beautiful pictures of the field, they were maybe 100 times smaller than the moon. In Atlas, the moon could fit many, 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 many times. So that allows us to go back to the same patch of sky every 24 to 48 hours, roughly, which means that we can actually find and track those near-Earth asteroids, but also we can find all of the things that go bang in the night sky that I'm interested in. So, as Lucinda's told you, I come from the world of people that study the things that go bang, so I could spend a whole hour doing nothing but that, but I don't have that sort of time, so we're going to focus on 3 kinds of explosions that happen in the night sky. The first one we're going to talk about is probably the most well-known, and it is the supernova. Now, supernovae are star explosions that were discovered in the 1930s. And in the last 100 years, astronomers have spent a lot of energy creating subclassifications of subclassifications of subclassifications of supernovae, which we will completely ignore today. Today, there are only two kinds of supernovae: the supernovae from low mass stars, born with less than 8 times the mass of the sun, and supernovae from high mass stars, born with more than 8 times the mass of the sun. So the low mass stars, supernovae, happen when a star like the sun comes to the end of its life and turns into what we call a white dwarf. That's an object that's about the size of the Earth, half the mass of the sun, and it has a very interesting property. If it gets too heavy, it explodes. And when it explodes, it creates most of the iron in the universe, and it gives you a light, a beacon that can help you track the expansion of the universe. And we're not going to talk more about this today, but someone got a Nobel Prize for this in 2011, so I promise you it's important. Now, the high mass stars are my personal favorite. They, first of all, are beautiful. This is the Crab Nebula. This is a real image, by the way. All of the pictures I'm going to show you today are either real pictures from telescopes or artist impressions made by people. None of this is AI generated. But this one is real. That's not CGI. So the high mass star supernovae happen when a high mass star gets to the end of its life, implodes, explodes dramatically, creates most of the oxygen, calcium, and intermediate mass elements in the universe, and leaves behind a neutron star, or sometimes a black hole. And here you can actually see the neutron star in the purple right there, and it's got a few jets because it's a neutron star on steroids, it's a pulsar. And that neutron star is really cool because sometimes they can go on to explode again. When neutron stars get a little too friendly with another neutron star, they create what we call kilonovae. This is an artist impression. We've never gotten that close. And kilonovae can happen not because neutron stars are minding their own business and suddenly encountering another one in the galaxy, but because massive stars are often born with friends. And so if you've got a binary system and both stars die, they can leave behind two neutron stars spinning around each other. These are the configurations of black holes, which we will mostly ignore today. And when you have two neutron stars spinning around each other, orbiting around each other, they create gravitational waves. And that's what's going to bring them close together. So gravitational waves, I think we've all got this image of the fabric of space-time that's been explained to us, where you picture an actual piece of fabric. And if you plop a heavy ball on that piece of fabric, you get a small well. Well, if you have two heavy objects next to each other, that well is no longer going to be circular. It's sort of peanut-shaped. And so if you've got these two heavy objects next to each other and that well that's peanut-shaped, and it's spinning in space, it's going to start wobbling the fabric and the fabric of space-time. And we can visualize this, hopefully we can, with this animation from Osgraph, and you can visualize the gravitational waves because of the way they distort the light in the background. Here we've got a neutron star orbiting a black hole. And as the gravitational waves are created, they tighten the orbit. So it brings the two objects closer and closer and closer together until eventually they merge. And when they merge, the gravitational waves die down because we now only have one object and not two. Now, if we want to see what happened to the neutron stars, we can look at this video. The gravitational waves are ignored in this case, or at least not visualized. But what you're going to see is that as the two objects come closer together, they're going to get stretched and squeezed, and they're going to turn into that teardrop shape, and they're basically going to tear each other apart. As some of the material comes together, a lot of it gets expelled outwards to space. Now in the center here, we've got a hypermassive neutron star that will turn into a black hole as soon as it starts losing its spin and angular momentum. But that material out there is really what we are looking for when we want a visual signature. That's what shines in the sky, and that's also where you create some of the rarest elements in the universe: platinum, gold, and the good old rare earth elements that allow us to make the technology that we use today. Now, the final kind of explosion that we're going to talk about is the tidal disruption event. That's the hungry black holes part of this talk. Tidal disruption events are probably the least talked about in the media, so it might be new to some of you. And essentially, it's what happens when a star gets a little too close to a black hole and gets torn apart. Again, we're going to use a video that I did not create to visualize this. Here we have a black hole with an accretion disk, and we've got a star coming in hot and coming in way too close to the black hole. And as it gets too close, it's going to get squished and stretched and spaghettified, essentially. And when it gets really, really close, it gets completely torn apart. Half of the material gets ejected. And as you can see here, the black hole looks like it's shining. Now, it's not the black hole itself that shines, because black holes are black, but black holes are not magical space hoovers. They don't just absorb the material all in one go. For the material to enter the black hole, it's kind of like, you know, the hole in the sink. The water doesn't just get sucked away magically. It has to spiral down into it. It's the same concept here, but there's so much material trying to enter the black hole all at once that there's essentially a space traffic jam in there. Just like real traffic jams, things get heated, and in space, when things get heated, they get really bright and we can see them. Now, the advantage of being able to see these things out in space is that how bright the light becomes and how it changes over time depends on the properties of the black hole. Its spin, its mass, and it allows us to probe black hole physics in a way that would be impossible otherwise, because black holes are black and they're impossible to make in the lab. So hopefully by now I've convinced you, by studying these gigantic explosions, we can learn a lot about our universe, the origin of the elements that we're made of, the expansion of our universe, and the physics of really dense objects like black holes and neutron stars. But in order to do this science, we first have to find these transients. Right, so a little change of pace, and we're going to try and do audience participation. This may fail. Can you see the difference between these two pictures? So these are the same. They're small portions of the picture of the Milky Way that I showed you earlier that I took with my phone. Now, some of you may notice that the picture on that side is blurrier than the picture on that side, and you can even see the pixels. Well, the difference is that the picture on the left is the raw image saved by my phone, and the one on the right is the JPEG saved by my phone from that raw image. Those of you that know how JPEGs work will find that very, very, very surprising. JPEGs are a lossy form of file compression. So if you take a file, a picture, and you want to make it smaller so that you can fit more pictures on your phone, you take the raw image, turn it into a JPEG. Normally, the resolution should be worse in the JPEG, but it looks like it's better. What happened? Why do we have more information in the JPEG than in the raw image? Well, it's because my phone is not a standard camera. It's on a smartphone that has a lot of software that can create, out of thin air, extra pixels. It's got magic maths to create more resolution. In other words, it's got generative AI doing the work for me here. Now, that's nice. But that brings us on to the AI part of this talk, where maybe the first question we need to ask ourselves is, what do we mean by AI? What do we mean by artificial intelligence? Now, I'm not going to go through the whole history of the word artificial intelligence. It's a very interesting one, but it's one that has more to do with people being people than to do with technology. Artificial intelligence is a word that has come into fashion and out of fashion through the 20th century and then back in the 21st. It's used in computer science, statistics, mathematics, philosophy, and psychology in slightly different ways, and it's used a lot on LinkedIn these days. But for the purposes of this talk, and most users of AI that you see in the world, we're really doing machine learning. That's what we're doing. Machine learning at its core is statistics. which granted doesn't sound as exciting as artificial intelligence, but this is the reality of what we're doing. We're using statistics to teach our computer a specific task. What we're doing is that we are learning a function, a mathematical function. There's going to be no maths in this talk, but we are going to have to use the concept of a mathematical function. So we're going to use an analogy for the concept of a mathematical function. And the analogy we're going to use is a DJ deck. Now, I've never used a DJ deck. I don't expect you to have either, but the concept is simple. You put music in, you twist the knobs and dials, a different sound comes out. A function is the same. You put something in, you change the parameters, a different output comes out. But in machine learning, we've lost the manual. And all of the numbers are rubbed out, and we have no idea how the knobs and dials work. But what we have is data. We have inputs, and we have an example of outputs, either a specific example of what sounds we want to make precisely, or we have an idea of what we want these sounds to do. Like we want people to bob their heads, or dance, or jump. We kind of know what the result should be. And using this, we're going to put music in. We're going to twist the knobs and dials until we get the result that we want. This analogy is heavily inspired by an XKCD from 9 years ago, where we have a stick man saying to another stick person, oh, this is your machine learning system. And then the person on the pile says, yep, you pull the data into this big pile of linear algebra. You can see a bunch of matrices there. And then you collect the answers on the other side. And then the first person says, oh, what if the answers are wrong? And then the guy says, just stir the pile until they start looking right. That is frighteningly accurate. It was accurate 10 years ago. It still is today. But there is method to this madness, I promise. What I think AI is on a societal level is that if you can teach your computer to do something you didn't expect your computer to do, suddenly you call it artificial intelligence. But it really just tells you about your expectation of what computers can do, not really what intelligence is. And I think a really good example of machine learning that would have been science fiction or was science fiction only a few decades ago, but is taken for granted today, is computer vision. Computer vision started getting kind of good in the 90s using something called convolutional neural networks. I can't explain to you what they are because that would take half a semester in an undergraduate degree. We don't have time for this. The point is, they started getting good in the 90s. Now, computer vision used to be the stuff of science fiction. Someone would walk into a futuristic looking building, walk up to a door, pop their glasses off, get their eyeball scanned, and puff, the door would open. And oh, that was the future. I can unlock my phone with my face. You take it for granted that Facebook can recognize your nan in family pictures. You know that a speed camera on the highway can take a picture of your car, read the number plate, and send you a fine. Computer vision is now something we take for granted, but for a long time it wasn't. Now, it started getting good in the 90s, like I said, and there was a bit of a lull. And it really, really took off in the 2010s. That's when we went from sci-fi to boring, we know Facebook can do it. And the big, big leap in computer vision came because of ImageNet. So ImageNet was a data set of pictures with labels, inputs with outputs. And it was 1.2 million of those images, and it was put out on the internet. And they said, okay, guys, anyone who wants to try it, train an algorithm, and then we will have a competition and we'll see who can beat the humans. By 2011, we already had a superhuman performance. And in 2012, we had the famous AlexNet winning the competition by such a large margin that it really helped the what we call the deep learning revolution take off. What was special with AlexNet was that it was absolutely humongous. 60 million of those knobs and dials in the function. LeNet 5, the reason this GIF looks so quaint, by the way, is because it's a genuine Yann LeCun from 1998. This GIF is older than students that we have coming into universities now. So this one had 60,000 parameters. AlexNet had 60 million. Basically, people realized if you make bigger models, you can get better results. And then big tech started hopping on the trends and things accelerated. The reason I'm highlighting Facebook AI Lab here specifically is only because of the AI Lab part. So artificial intelligence in the early 2000s and 2010s, not a good word to be throwing around. Everyone was saying machine learning, deep learning, that kind of stuff, because AI had been used a little too much in the late 20th century, overpromised, underdelivered, and you sounded like a bit of a kook if you said AI back then. But Facebook reclaimed the word, and here we are in 2025 saying here, AI this, AI that. So the point to take away here is that machine learning breakthroughs happen when you have two things coming together. At least historically, that's what's happened. Data and compute, access to data and access to compute. For computer vision, there was a perfect storm. By the 2010s, people had been on social media for several years. People already had phones in their pockets, taking pictures of their face, sharing it with everybody. So there was a lot of data out there. And the compute was getting more readily available. Graphics processing units, GPUs, are really good at linear algebra. That pile of stuff, the stick figure we're standing on, that's the kind of maths we need to do machine learning. And these were becoming more readily available because of the video game industry and because of the CGI industry. But what that meant for astronomers is that you can take pictures and you can have your computer classify them for you. Now, it is not sci-fi anymore. You can teach a computer with maths to recognize your pictures. Okay, let's play spot the difference again. This one's going to be trickier. In the crosshairs, you may see a fuzzy thing. The fuzzy thing is a galaxy. Now, it's really hard to see in this setup, but there is something extra in the after picture. To make it easier to spot, I'm going to remove the before from the after, and there you go, bam. We've got a blob. Admire the blob. The blob is a supernova, and it is the kind of stuff that we are looking for in our sky survey. So difference imaging, that's what we're doing here. You take an observation, you remove a reference, and you look at the difference and see if there's something left. The problem is difference imaging is not always this clean. It is often nasty, especially in very crowded fields. Here, there's no difference between the before and after, but in the difference, you can see a lot of noise, a lot of false positives. In Atlas, we get of order tens of millions. So, 10 to 15 to 20, not like 70 million, but like millions and millions and millions of potential alerts every night, and only a handful of cool new explosions. It would take a human 6 months to a year to analyze the data for one night of Atlas. And that means that we have to automate. We have to hire our computers to do some of the job for us. Now, when we automate stuff, we don't start with AI. The first thing we do is basic cut. In Atlas, it's pretty simple. The most basic thing to do is make sure that stuff is bright enough to look realistic. Also, because Atlas takes 4 pictures of the same patch of sky every night, we can say, okay, if you can see the alert in all 4 pictures, you're good. If you can see it in 3 pictures, you're good. If you can see it in 2 or just 1 picture, good, stoop the bin. That does a lot of the job for us. The next thing you do is you check for known variables. If you're looking for supernovae and near-Earth asteroids, you don't want to find Betelgeuse every night. So you remove it and all its variable friends. And then when you've done that, you're left with a few thousand, maybe tens of thousands of alerts. Still too much for people to do on their own, but there we can start employing some machine learning. So our convolutional neural network is trained specifically on the difference image. It looks at the center of the difference image. And so that's the input. And the output is a number between 0 and 1. 0 is bogus, 1 is real. It could be anything between 0 and 1. And what we say is if an alert has a score of 0.2 or below, it goes in the bin. 0.2 and above, we're going to look at it. And by doing this, you can remove 98.5% of the garbage, which is great. but you still have hundreds of alerts to look at. And historically, that's what people had been doing with their eyes. We call these people eyeballers. I'm an eyeballer myself. And what you would do is that you would sit at your computer, and for a shift of about a week, you would spend every day looking at a few hundred of these alerts. And you would split them into garbage, or various kinds of garbage, or real galactic event, or real extragalactic event. Call them good because I'm biased. The galactic stuff is good too, just not better. And that would take you maybe a couple hours a day. That's a couple hours of astronomer time wasted to just looking at mostly garbage. But automating this is complicated because eyeballing is a complex task. You're not just looking at one picture. You're looking at, where's my stick? You're looking at the pictures. You're looking at a light curve, in this case, 1 point and a bunch of non-detections. You're looking at where it is on the sky. Those are the coordinates. You're looking at some contextual information. Does it have a known source nearby, like a known galaxy? How far is it from that galaxy? And using all of this diverse information, people can make really good decisions really quickly, even with just 1 point in the light curve. People are impressive. We have fantastic pattern recognition machines in our heads. And it's sometimes very hard to make computers rise to that challenge. But with the VRA, the virtual research assistant, that's what we tried to do. And we tried to do this by having the virtual research assistant follow a very similar strategy to the humans. You ask 2 questions. Is it real? And if it is it galactic? And by doing this, the virtual research assistant can rank the alerts that come into the eyeball list, and it can crop the vast majority of the bad. Now, the virtual research assistant does not make the decision on its own of this is good and this is galactic. And that is because if we say that something is good, if we click on that button, we send an alert to other astronomers and we say, hey, put this in your database, this is the real thing. We do not want to delegate that level of responsibility to a machine, but it is nice to have most of the bad being cropped away and then have humans look at what's left. So you go from hundreds of things to look at a day to a couple dozen, basically. And it works. That's not just theory. I did it. This is a plot from last week. So the gray stuff is the virtual research assistant. It bins 83% of the stream we had that week. 6.3% was labeled galactic by the eyeball. That's the same number. It's not always the exact same number, but it worked out that week. Good stuff, about 4.15%. It's a bit lower than this, but it's because the moon was really bright last week. We just don't see as much. So yeah, it's working. And people have to do only 13% of the job that they used to have to do. So how does it work? Well, you're just learning a function. The algorithm I'm using has a very horrible long name called histogram-based gradient-boosted decision trees. It's just a thing that teaches a function. The inputs are similar to what people look at, but obviously our machine doesn't look at a web page. I have a way of giving it the information, but it's looking at the light curve, it's looking at the location, it's looking at the context. It gets the information from the CNN. And then the output, like I said, is it real? Is it galactic? And with those 2 questions, those 2 numbers, we can put our alerts onto a graph like this. So the bottom is the real score between 0 and 1, and then the y-axis, the galactic score between 0 and 1. So stuff that is real and extragalactic stands in that corner, and then stuff that is real and galactic stands in this corner. But like I said, the VRA does not classify for the humans. It ranks the alerts. So how do you go from this plot to an actual rank? Well, to do this, we're going to use the newfangled technology of the Pythagoras theorem. We're going to calculate a geometric distance to this corner of the plot, because that's the one that I care about, and that's the one that my colleagues care about. So you take that distance, and you add a couple of fudge factors so that a short distance means a high score, and then you add another scalar so that the scores go from 0 to 10, because that's a nice number. And you get an ordering of the eyeball list that is really useful to people. And then you can crop the list below a certain rank and say everything below that is garbage. And that's how you get this, by combining technology from 8 years ago with technology from 4,000 and probably before, from thousands and thousands of years ago. So maybe I should amend my statement that I made earlier. Progress in modern astronomy and science is the combination of people and the right technologies. And the right technologies don't have to be new. If it works and someone figured it out thousands of years ago, you can still use it today. Right. In the final parts of this talk, we're going to address the elephant in the room. I have not mentioned ChatGPT or DeepMind or DeepSeek or Gemini at all as of yet. And I thought we could have a little party at the end. Right. Can you tell me what this is? This is an image that was taken with this very phone that took the beautiful image of the galaxy that we saw earlier. This is a zoomed in, cropped out bit of a larger picture that I took of an announcement board in Venice when I was stuck in an airport for 7 hours due to a strike. I wanted to check how delayed my plane was, and because I can't see, I took a picture to try and zoom in and get the information. The problem is that the smart software that made the picture of the galaxy more beautiful than it could be also jumbled up the words in the picture. The reason that happens is because, it's an educated guess. I don't work at Google, okay? This is an educated. But these algorithms that are made to make your pictures more beautiful are trained to make landscapes, to make faces prettier. These things rarely have tiny detail with very sharp right angles and straight lines. The sharp angles and straight lines come from the pixels usually. So these have to get smoothed out to make the picture prettier. But in this case, although the picture I'm sure is prettier in general, the one piece of information I was after was destroyed by the smart software. To understand exactly why that kind of stuff can happen, we're going to look at another anecdote of machine learning breakthroughs that happened recently. So in 2016 was another milestone that was broken. AlphaGo by DeepMind beat Lee Sedol, the reigning champion, at Go. Go is a game that is very complicated and a lot harder to train machines on than chess because there's just so many more board possibilities. That was a big deal. AlphaGo won, fine, thousands of CPUs, hundreds of GPUs, fair. But Lee won one game. He beat the machine once. And he beat the machine because at some point in that game, he made a move that had a low probability, that was unexpected by the machine. And from then on, the machine started making really bad decisions. This can happen, your model making bad decisions because it sees something unexpected. Because when you're training a function, a large function, you're exploring how twisting all of these knobs and changing all of these parameters, how that reacts with each other. It's a little bit like exploring a map, like discovering new frontiers. This is a screenshot of Civilization 5, for the game is in the room. A game in which one of the things that you do is you explore a map, and the bits of the map that are not explored are in the fog of war, so you can't see it. And so learning a function is a little bit like this. You explore a map, and the bits of the map that are not explored are in the fog of war. The problem is when you have models that have millions, billions, trillions of parameters, there are many, many of these areas. These are called they've been coined as Sidonian voids by Neil Lawrence. I don't know how much this is catching on, but this is a fantastic book. And Neil is a very respected man in the machine learning community. And in honor of Lee Sedol, who put AlphaGo in one of these voids. And basically, the notion is when an algorithm is put in one of these voids, they start to behave erratically or they fail catastrophically. Why is that a problem? Because I care about the rarest, weirdest objects in the universe. So it is not likely that I will put my algorithms into a situation they've never seen before. So picking algorithms that can behave erratically or fail catastrophically when that happens is not ideal. Now, the other problem with generative AI, the kind of stuff that creates sentences or creates images, is that they are probabilistic models, which means that if you put the same input in the model several times, you'll get different results. If there's any statisticians in the room, I know that probabilistic models are not necessarily an issue, but the problem is if you don't have access to the models themselves to know what the posterior of the probability function is, then you're a bit screwed. The third problem, especially with LLM, is that although they sound great, they're trained to sound like people, they're not trained to be truthful. So they're very problematic in scientific context. So problem number 2 and problem number 3 are of particular concern if you're a scientist, because reproducibility is key to my job. If what we're doing is not reproducible, we might as well be doing astrology. So we need to be very careful with these things. And I guess the point that going back to this statement, progress is a partnership between people and the right technology. As we've seen, the right technology can be all technology. What I want to emphasize right now is that new technology is not necessarily right. New technologies are a new opportunity for discovery, but discovery is not an inevitability. Progress is not an inevitability when something is new. Just because a specific kind of technology has been very helpful in one field does not mean it will unlock a revolution in another. We have to be as skeptical as we are passionate. We have to take these tools, try them out, try to make them fail, push them to their boundaries, see where they misbehave, so that we really understand what they can bring us and the problems they can bring with them. The final thing I'll say is that the right technology, yes, is understandable, yes, is reproducible, but I would argue it is also sustainable. Now, sustainability is a big thing. I am probably not the best person to talk about sustainability in general, but the reason I will mention it is because, as we saw earlier, machine learning breakthroughs in recent history have come from large amounts of data and large amounts of compute. Large amounts of data and large amounts of compute require large computers or large data centers. Those are out of sight and therefore often out of mind, but they require a lot of electricity and a lot of resources that have a human cost and an environmental cost. Machine learning is the thing that you do when everything else has failed. Making a big model just for the sake of a big model is not science, and it can have negative consequences for the world that we live in. The reason I wanted to mention this is I want us to be conscious of the planet that we're on, even when we look up at the heavens. All right, enough moralistic tone. I'm going to move on to the thank yous. Thank you to Kenson, the Seven Wizard who keeps Atlas and other things afloat all day, every day. He's also my partner in coding crime. A big thanks to my mentors, Stephen Smart and Stephen Roberts, in particular Stephen Smart, without whom I wouldn't be here today. It took 10 grant rejections to get the job I have today. A year and a half to 2 years of not knowing what my next gig was going to be. And he still believed in me when I didn't anymore. A big thank you to the Herschel Society for the prize. A big thank you for the Royal Astronomical Society for hosting us. And of course, a big thank you to you all for being here today.
Time for questions now.
Do we have any questions?
Hi, thank you very much for this one. With the VI models, you applied that to what have already been pre-filtered, right?
Yes.
Have you applied it to the total amount of data before filtered just to check that your assumptions were correct, or are you very solid on the assumptions that you made? You won't skip them.
That's a good question. So the reason, so I didn't check it on the other stuff because not all of the data is there. So so when we are here, when we do the cross check to see a bit of this, we also add new information to the stream. So the contextual information, like is there a galaxy nearby? How far is it, etc. The kind of stuff that people use to make decisions only gets into the stream here. Also, the information from the CNN, like the score this gives, is also an input for the VRA. So basically, the concept of the VRA is to say, if you have the exact same information available to you as the people, how much smarter can your decisions be than if you try to just do it with one picture or that kind of stuff. As for checking stuff, we are very careful because otherwise we could miss a supernova. So we have training data that has, inputs and labels from people. Basically, what we do is we split this into data that we use to train the model, and then data that the model does not see that we can use to check that our predictions are correct. That's the plot that I showed you. It was on data that the model was not trained on. It was on data that was used just for validation.
Thank you so much. And a very quick one as well. So when I take a photo of the moon with my phone and it looks rubbish on my lens, but the photo looks amazing, is that also the same thing?
It could be that. I've seen people claim that some iPhones just get a picture of the moon off the internet and just pop it in the picture. Maybe. I mean, I think knowing exactly what the software does is only possible if you're the one writing that software and you're one of these companies, and they will never tell you exactly what they do because it's a private market.
Request that you can repeat the questions for the Zoom audience.
Yes, I will do that.
Great tool, thanks. Since you've been using this, what has been the payoff to these transient events? Have you been able to, or have other people as a result of your work been able to observe more super revive type of disruption events? Has there been an increase?
So the question was, what's the payoff from using something like the virtual research assistant? So there's two payoffs. One, if expert time is precious. So if you can save 80% of that and they can spend it doing data like analysis, because we have more events than we have resources to do. So that's nice. The other thing is we've been able to start automating more of our processes. So for example, there's a telescope in South Africa that has an instrument called Makodi. And what we've been doing recently is we've started automating triggers. So if something gets a VRA score that's high enough, it automatically gets put into that queue, because South Africa being basically similar in longitude than us. I know this. The problem is if an alert looks good, and then you have to wait for a human to be awake to say this is good, then you have to wait for the night in South Africa to observe it. You've got a latency of 24 hours, when if you have just a VRA and a piece of code, you can have a latency of a few hours.
Yeah, it's just really quick, great talk by the way, but phones definitely do this by Samsung phone. If I zoom in on the side, you see craters, stuff, little tiny ones. Not result, but it's a nice picture.
Yeah.
It's clear.
Yeah. We've got confirmation that Samsung phones are cheating.
So maybe the Samsung just reduced the coin.
Yeah. Well.
I really feel like I can tell my students now. There's an example for when you can actually use the
Yes.
I have a question online. Just curiosity of what on your eye about high mass stars? Why did you go to this field of study?
What's caught my eye about high mass stars? I fell into it, and they're close to my heart because I studied them during my PhD. I studied them during my first postdoc. The pictures look better. The type one is the low mass stars one are always round. The crab is beautiful. That's the picture that I showed you with the neutron star in the middle. It's completely unbiased. It's completely biased. It's completely subjective. It's not a scientific opinion. It's a personal opinion. High mass stars are the best. You've heard it.
Any questions in the room?
Thank you so much for your talk today. Thank you. There are still, if you still want to ask your questions while you're here, I know there's some time about the online. But we also have a wonderful exhibit upstairs in our library. So please, you go to let's go on. Thank you. Thanks.